Okay, this is term 2, week 6, uh, physics, CA. You know that it's with the new timetable that we have agreed on. We will not have applied math mechanics CA this week since it's an even week. It's going to be 40 minutes of a physics CA, which is obviously going to be a longer exam. So ideally, we have now added the PISA material, whatever you want to say. So there will definitely be questions from PISA in the exam. So just so you know, with it being 40-minute exam, obviously material is longer. So most of this is repeated, but we have from 4.4.3 until 4.5.10. Sorry, 4.5.3 until 4.5.10, which is new. So I'm gonna start now. I don't have notes on it because I was absent, and then chapter 6 I do have notes on it. So I'll open that in a second. Anyway, let's start with 4.5.3. I'm gonna go through these very quickly because they're all so much talking. I'm just gonna talk about the important things of over here. The importance of the earth wire, I'm gonna skip it all. Basically, you guys know the earth wire is the protective one. The protective one, as in the earth wire protects the cable. Let's say, for example, you have this circuit here, and for some reason, this wire that's connected to the motor actually disconnected and was attached to the machine case. If this machine case is a metal, that means if you touch this metal, you're going to get electrocuted. So what does the earth wire do? If it detects any electricity, it basically it has a fuse. You guys remember fuses from last week. Fuses, if they detect anything wrong, they melt and the circuit closes, right? So there will not be any more circuit. It opens and there will not be current passing. Okay, so that's how the earth wire works. When it detects current passing through the wrong places, it causes a fuse that will melt and cut off the power supply. Then selecting fuses and circuit breakers is very easy. We had this earlier. Like, remember when we had the 4.6 ampere lamp? They would tell you what fuse would you use. Obviously, if it's a 4.6 ampere, you'd use 5 ampere. Okay, so you can read over this if you want. It's simple. Power classification, there's low, medium, and high. Low power is computers, any electronics are low power. Okay, and also cassette players, videos. These are all low. And then medium power requirements, TVs, hi-fi systems, small refrigerators. High power, obviously anything that has heating or cooling or any motor, like heaters, electric cookers, electric kettles, coffee makers, washing machines, freezers, air conditioners. These all require high power. So this is all Hebel. I'm gonna read over this just in case it comes because it's in blue text. A poor contact between two wires means that the area of contact is less than the cross-section area of the wire. If the area of contact is less than the cross-section area, if there's poor contact, okay, what you need to know is a poor contact means that the area of contact is less than the cross-section area of the wire used. Why do we care? If that's the case, that means the resistance is very high. Okay, that's all you need to know, and this will cause a fire. Okay, you can read over this if you want. Okay, this stuff comes in exams. This picture over here and this picture over here, which I'll show you in a second. So as you can see here, this question and this question, they both come in exams. Drag and drop, of course. So you need to know that there are color codes for the wires. You know, we have live, neutral, and earth. We have old appliances and new appliances. In the file, it says European standard and British standard. So what they did, our nice, lovely exam writers, in the book, it's British standard, then European standard. Here, it's European standard, then British standard. Okay, so let's try and figure out a way to memorize this. But obviously it doesn't really matter because into what you're labeling is the top part. Hold up, you're labeling the top part. Okay, over here, see, in the exam you're only labeling the top part, but in case they ask, know that the British ones are RBG. Yeah, RBG is British, and for the European it's brown, blue, green with yellow stripe. The one with green with yellow stripe, I remember it as the European. Anyway, the live wire, the easiest one to memorize is the neutral wire, in my opinion, because it's black as if there's no current passing because it's neutral. And then earth wire, again, the easy way to memorize it. Earth is green with yellow stripes, so you can memorize it easily. And then the live wire is just red, brown. Okay, so the live wire, is the source, obviously, of the electric energy. It's the one that's alive, okay, from plus 340 to minus 340. The neutral volt, it's very easy. It remains ideally at 0 volts. It's the one. It just carries stuff back. There's nothing passing to it. It just carries any current path back to the circuit. Then the earth one, obviously, is the one that carries current outside. Okay, uh, you can read over this, but you need to know that wires that don't have an earth wire, any circuit that doesn't have an earth wire, is actually called double insulated, and this is what double insulation has its own section. If you see the symbol double, it means it's a domestic appliance. That means it's double insulated. These double insulated appliances always don't have an earth wire. They don't have an earth wire. That's what you need to know. Okay, and they require a twin cable. I'm sure you guys have seen, like you've seen chargers in other countries where they don't have this. It's just these two. I'm sure you've seen it before. Okay, you can read over this. There's all extra materials. I won't go over it. Again, over here, it's wiring a fused 3-pin plug, whatever. This picture is what you need to know. It was also here. Obviously, this is the earth wire, and the neutral wire. Remember, it was either blue or black, right? Either blue or black. Okay, and the live wire is brown or blue. Sorry, as is brown or red. And the wires are easy, and then obviously the fuse is inside and the cord grip. The fuse, obviously, remember, the fuse always has to be on the live wire. Remember from the last section last week, it's required also for this week. Where do you place a fuse? You always place it on the live wire. You're not allowed to place it anywhere else, right? So the fuse is always on the live wire, and the cord grip is over here. This is the cord grip, yeah, the thing you hold, yeah? Which, this is very straightforward. There's nothing hard here. Just labeling. You can read over this if you want. Again, I won't go over it. This is earthing transformers. Again, I'm not gonna read over this. It's all easy stuff. So all they're talking about transformers, I just read it quickly, is they both have their own live wire, earth wire. Like, remember how we have a primary and secondary? Yeah, they both have their earth wire and live wire for the first, and earth wire and live wire for the second. But you need to bear in mind, if you're using a transformer, that the currents are different, so you're gonna have to think twice when you're choosing the fuse that you want to use. Yeah, because remember, the current here is different than the current here. NS over NP. This is the formula. They're asking in the book that you should know the symbol here. This symbol, all you should know is that this is a transformer. This one in the middle, the line in the middle, is just the metal core, the iron core of the transformer. And obviously the one on the left is the primary coil, with the one on the right is the secondary coil. Okay, and then filament lamps versus fluorescent lamps. Just know there's a lot of convection. You want to read over this, read over it, be my guest. But basically, all of this, it says that filament lamps work on alternating current, and alternating current looks like this. And there's points where there's zero, and then people go like, okay, so why when I look at my lamp, it doesn't turn off every, I don't know, every 100, like, why doesn't it turn off? It should turn off because it hit zero, no? And then someone will be like, okay, no, it's because filament lamps work on, you need to know this. Filament lamps need to know, what? Filament lamps work on the principle that the filament is heated to incandescence. Incandescence basically is, it's too hot, okay? So when the current drops to zero, the filament lamp will not have time to cool down to lose the incandescence, so it remains it all the time. The filament lamp heats up gases. Those gases are what gives off the light. If you read this, you'll understand. But basically, you heat up these gases. So in this 0.001 milliseconds, it won't have time to cool down and the gases to turn off their light. That's it. That's why, by the way, when the lamp runs out, it's because there's no more gases. That's how I remember it. Okay, then do's and don'ts with electricity. I'm not even gonna. You can read this if you want. Pause and read if you want. I'll zoom in, be my guest, and read all of these. But I think these are all very, very, very straightforward. And you do not operate equipment in damp, like, no shit. That's very obvious. Do not take high rated power appliances like hair dryers into bathrooms, because there's a risk of getting, okay, I think if I got my little brother, he would know this as well, so it's not that big of a deal. Let's start with 6.1 now, waves. We have a lot of, why I'm going fast is because we have a lot of sections repeated from last week. 6.1, a pulse is a disturbance that travels from one location to another. A wave is a train of pulses, okay? So any disturbance is a pulse. These are all blue texts in the book. Huh? In pulses, energy is transported with the pulse along the medium itself. You need to know that energy is transported with the pulse. Matter itself isn't transported. One way to remember this is the sun. The sun gives off electromagnetic waves, right? The radiation waves. We know that we get heated up by the sun, so it actually transports energy, right? And you should also know that the sun is the sun traveling down with the wave? No, it isn't, right? So that's actually a good way to remember. Anyway, okay, we now have these two, transverse and longitudinal waves. Please know how to spell longitudinal. I spelled it wrong here. I spelled it correct. Not here. This is also wrong. No, I didn't write it correctly. Somewhere. Okay. Yeah, longitudinal here. Longitudinal with an I. Okay? Know how to spell it. Anyway, transverse waves and longitudinal waves. Basically, a wave, there's two different types of waves, transverse and longitudinal. What differentiates them? Transverse waves, it's where the particles, they move normal to the wave. So if the wave's going like this, it's pushing to the right, yeah? The particles are gonna move up. See how it's perpendicular? It's normal, okay? An example of this is an ocean wave, okay? An ocean wave is a transverse wave because the particles, the waves, the actual ocean waves, if you were like, if you had a boat, you know how you go up and down and up and down? That's what an ocean wave is, and kind of looks like it, okay? So when it goes up and down, or normal, you can't see up and down in the exam, you have to see normal, so perpendicular to the wave, then it's called transverse, okay? A longitudinal wave, it's where particles of the medium move parallel to the direction of the wave, okay? For example, sound waves. Sound waves are vibrations. You know, they're vibrations, you cause vibrations in the air. Sound waves, sometimes they come out strong, sometimes they come out weak. You know, like there are small areas where it's louder than others. So you can think of it like this, okay? A sound wave comes like this. This is the wave. It has areas where it's wider and areas where it's compressed. These two have their own names, which I'll get into in a second, but 1 second. The most important part here is that the particles move parallel to the direction of the wave. The wave is moving to the right, yeah? The particles either move to the left or also move to the right. In this case here, they move to the left. They moved up, like over here. In the part where the wave is moving like this, in the part here where they widened up and they moved away from each other, obviously it moved parallel but backwards to open up, to widen up the gap. In this case, in the right, however, the wave is moving to the right. The particles themselves also moved to the right and they became tight and compressed, you see? These two phases are for longitudinal waves and they're called rarefaction and compression. Compression as in they're tightly packed together and compressed. Rarefaction as in they're wide, they have space. 6.2, okay, you need to know that sound must pass through matter, such as solids, liquid, and gas, and not vacuum. I meant not vacuum. Fix this out, not vacuum. Okay. I should send an announcement about this. Okay. So I sent an announcement now. Sound is a longitudinal wave motion that is mechanical, and it needs a medium to travel through. If something is a mechanical wave, it means that's in the next point. But this definition must be memorized. Word for word. It's something they ask word for word. So sound, you need to know it's a longitudinal wave that is mechanical and it needs a medium to travel through. When is a wave considered mechanical, like sound? If it needs a medium to propagate through. If it doesn't need a medium to propagate through, then it is called an electromagnetic wave, like light. Okay? This is an example of rarefaction and compression. You have a speaker over here, and these are air molecules. When air molecules are spread out and have white spaces between them, it's called rarefaction, and there is low pressure. This is the pressure. There's low change in pressure. When it's compressed, obviously there's going to be high pressure because they're all packed together. And again, low pressure when it's spread out, and then compressed, high pressure. So rarefaction is when there's less accumulation and less compression. Okay, obviously, and it happens when there's low pressure and maximum displacement. There's more displacement, obviously, because they're spread out. They're further away from each other. Okay, a compression is tight and cramped, right? And there's maximum pressure and there's low displacement because they're very close to each other, not far. A progressive traveling wave is a disturbance that carries energy away from the source from one place to another. That's just a definition. These two are important. In the same medium, under non-changing conditions, you need to know that waves and pulses move at a constant speed in non-changing conditions in the same medium. Pulses moving in the same medium have the same speed. So every sound wave in air has 341 meters per second. Every sound wave in water has approximately 1,500 meters per second. Light, same thing, 3 times 10 to the power of 8. And water is 2.2 times 10 to the power of 8. Because don't forget, light is also has a wave nature, right? Light behaves as a wave. All electromagnetic waves travel in vacuum at speed c. C is 3 times 10 to the power of 8 meters per second. And this is not important, but anyway, let's start with the quiz, okay? We're gonna fly through this. What is sound? Sound, we said it's a longitudinal wave motion, and since it's mechanical, it needs a medium to travel to. Must be memorized. Question 2. Which of the following describes a sound wave in air? Sound, we said it's longitudinal and mechanical, right? Okay, these are easy. Which one is the one that induces the EMF? We know it's a secondary coil in the transformer. Remember the transformer, you have the primary coil and you have the secondary coil, right? Which one actually induces the EMF to the circuit? It's this one here, right? Which helps link it, the soft iron core, which generates the magnetic field, its primary coil, right? You should know that the magnetic field is alternating, it's variable, and EMF is also variable. It was a question. A transformer has 760 in the primary and 100 in the secondary. So what is it? Step down or step up? Obviously step down, since the secondary coil has less turns. Question 5. In order to decrease loss of energy in power transmission, certain measures must be taken in the national grid. The amount of loss of energy is proportional to the square of the current in the wire, right? P is equal to Ri squared, right? This resistance is fixed, so we care about the I squared. In order to decrease these losses, step-up transformers are used. As a result, the grid transports electricity at high voltage. So we use step-up transformers to increase the voltage, right? And when you increase the voltage, that means there's lower current. And when there's lower current, that means there's less energy lost. Okay? Question 6. The peak, we have primary, secondary, and the primary one is 60 turns, and there's N in the secondary. The peak EMF in the primary and secondary coils are 48 volts and 240 volts. What's the number of turns in the secondary coil? Obviously, V out over Vn is equal to Ns over Np. So V out is 240, right? Vn is 48 volts. Ns, we're trying to find the secondary coil. Over Np, it's 60, right? So obviously this is going to be 300 if you cross multiply. The current in the primary coil is 4 amperes and the current in the secondary coil is 0.72 amperes. What is the input power of the transformer? P is equal to IV, right? So the input power is equal to the input current in the primary coil, 4, times the input voltage, 48, which should be 192 watts when you multiply them. The output power, P out, is equal to I out, V out, right? How much current do I have going out? 0.72. How much volts do I have going out? 240. Multiply them, you get 173. How do you find efficiency now? It's power out over power in times 100, which is 90% when you do it. 173 over 192 times 100 is 90%. Okay. We have the circuit breakers. We need to label them. I just need to make sure my mic is on. Okay. Which one protects people from accidental electrocution? Obviously, it's the earth leakage because it's leaking electricity. Protects from overcurrent by melting down. It's the fuse. Protects from overcurrent, should not be replaced after the event of an overcurrent. So the fuse and the electromechanical circuit breaker are both protecting from overcurrent, but the difference is that the fuse melts and the electromechanical circuit breaker is something that shouldn't be replaced. Yeah. Question 8. A 0.8 kilowatt washing machine works on 220 volts main supply. The current flowing through it is 3.6 amperes. Which of the following fuse should you use? Obviously 4 amperes. You shouldn't use 5 amperes, not 20 amperes. No, you need something that's close to 3.6 but still above 3.6. You can't use 3.6 exactly because if there's a small fluctuation, then the fuse will melt, even if it's just a tiny fluctuation. What's the efficiency of the transformer here? Remember, efficiency of a transformer is P out over P in times 100. P out, it's in milliamperes, so you need to make it amperes. So 0.162 is the current. Remember, P is equal to IV, huh? So 0.162 is the current times the volts 110. So that's P out. Let's do this on our calculator. We get 17.82. And over here, when you do P equals IV, 2.2 times 9, you get 19.8. So P out is 17.82 divided by 19.8 times 100, you get 90%. Okay? Question 10. A water wave can be generated by continuously tapping on the surface as shown below. What is a wave? Waves are vibrations, right, that transfer energy, right? Not matter. They transfer energy without matter, right? The matter stays where it is, but we only transfer energy. Okay. The sentences in the table describe different regions in a sound wave. Row A, row B. When are they spread out? In rarefaction. When are they closest together? In compression. These are the alternative. The diagram below shows the variation of pressure of a sound wave in air at one instant with respect to distance. Which point describes the description in row A? Row A is rarefaction. When do we have rarefaction? We have rarefaction when there's the least pressure, so Z. And row B is compression. When do we have the compression? At the highest pressure, so at X. Okay? In question 12, a wave in which the displacement is along the same direction of the propagation, it's longitudinal. If they said parallel as well, that would be correct. And in a transverse wave, particles move in a direction normal or perpendicular, right? In transverse wave, remember that the movement of the particles is normal to the wave or perpendicular to the wave. Question 14. The input voltage of an ideal transformer is 12 and the number of turns is 100. The number of turns in secondary is 650. What is the output? Of course, V out over V in, which is 12 volts, is equal to NS 650 over NP 100. Remember, V out over V in is equal to NS over NP. Type. So if you cross multiply, you should get 78 volts. Based on the number of turns, what is this? It's obviously a step-up transformer, right? Step up, why? Because more secondary turns than primary turns. Question 15. A step-up transformer obviously increases the voltage. An ideal transformer, what does it do to the power? Remember, ideal transformer, what categorizes a transformer as ideal is that it doesn't change the power. The power in is equal to power out. A real transformer, not ideal, a real transformer, there's always going to be power lost. So for that reason, it decreases the output power. If there's power lost, then the output power is less than the input power. If a transformer increases its output voltage, then obviously the current will be decreased. And why do we use this? We use this to decrease resistance in the national grid, right? We increase the voltage using a step-up transformer to decrease the current. 16. Drag and drop with... Obviously, the heaviest one is the supergrid. The supergrid, remember, it's at... Let me see over here. As you can see here, the supergrid is the highest. Then what did they say? After the supergrid is the normal grid, and then goes to the heavy industry, the light industry, and the towns, right? So over here, the maximum is supergrid, then it goes to grid, then heavy industry, then the power station output. The power station output over here, the power station output is only 25 kilovolts. So out of all of these, it's the least, except for the towns over here and the light industry. So if they put light industry, the power station output will be more consuming than the light industry, as you can see here. Okay. So supergrid, grid, heavy industry, power station, light industry, transformer. Question 17. An electric heater is labeled 240, 50, 2000. The label also states that the appliance must be earthed. What part of the heater must be earthed? Always, the thing that must be earthed, remember when we did the earth wire, is the metal casing on the outside. Why do we earth it? So that when you touch it, you don't get electrocuted. Okay? The heater contains a standard electric fuse. Where is the fuse placed? It's always placed on the live wire. And then they say, what is the label on the fuse? How many amperes? How do you calculate it? You have the power, you have the voltage, and you know that P is equal to IV So I is just going to be equal to the power 2000 divided by the voltage 240. So let's do 2000 divided by 240. And you get 8.3. Did I do something wrong? Okay, so you get 8.3, and the closest answer to 8.3 is 13 over here. So you're going to use 13. And since it's an electric heater, okay. Since it's an electric heater, it's high power. Remember in the ebooks, we saw that there's a low consuming, medium consuming, and high consuming. Electric heater is high consuming, so there should be not a 0.5 gap. No, there should be like a good gap, 4 or 5 ampere gap between the fuse and the actual heater. Okay, because since it's high power consuming, you're gonna see a lot of current fluctuation in it. Okay, so let me go back to the. Can I go back to the answer? Okay, well. Okay, question 18. You have a new domestic appliance includes a 5 ampere fuse. The fuse protects the wiring when what does the fuse do when there's too much current? The fuse installed on the wire whose plastic case is colored what? It's installed on the live wire. Remember, the live wire is either brown or I think it was brown or red, right? Let's take a look. It's actually here. I have it here. The live wire is brown or red. Yes, live wire is brown or red. Yeah. Okay, when the fuse blows, what happens to the circuit? Obviously, it disconnects the circuit. A house appliance is labeled 220 volts, 4 kilowatts, and is protected by a correct fuse. The electrician of the appliance replaces the original fuse with a 5 ampere fuse. Which of the following will happen when the appliance is switched on? Let's see. What is the fuse they originally need? P is equal to IV, so let's see. P is equal to IV. How much current do we need? I is equal to P over V, so 4000 divided by 220. Why 4000? Because it's kilowatts, so you multiply by 1000. 4000 divided by 220, and we get that the current needed is actually 18 amperes. So if you use a 5 ampere fuse, now we need 18 amperes. So obviously when you turn it on, it's gonna deliver 18 amperes, and the fuse is gonna recognize more than 5 amperes. So what's gonna happen? It's gonna blow, and the appliance is gonna turn off. Does the appliance get damaged when the fuse blows? No, but you only need to replace what? You only need to replace the fuse itself, because obviously it's blown. But the appliance itself is fine. Consider the following fuses. The lowest current label on a correct fuse that should be installed is what? For here. Yeah. Which correct fuse would be would be good? Obviously it would be the 20 ampere one. It's the closest to 18. 25 is too much. Question 20, just label. A train of pulses is obviously a wave. A disturbance traveling through a medium is what we call a pulse. The point along the wave corresponding to the maximum displacement, so when they're the furthest away, obviously rarefaction. 21. The diagram below shows the displacement of soil during the propagation of a wave along the surface of Earth after an earthquake. What kind of wave is shown below? Longitudinal. Why longitudinal? Look here, you have compressed parts where the lines are very close together, and you have parts where they are further away than usual. So when do what is this an example of? Compression and rarefaction, right? And when do we see compression rarefaction? Only in longitudinal waves. Okay. Part B, underline the points at which compressions are observed. Obviously over here at 1 and at 3, and then they said circle where you have rarefaction, obviously at 2 and at 4. Not at 5 because here it's normal, but at 2 at 4 you have rarefaction because they're widely spaced. You see? So we're done the quiz, but we still have the grid questions. You do them yourself, but we need to do PISA, okay? Because many people forgot it, and I'm sure we're gonna get 4 or 5 questions from it. Okay, so let's see PISA science. Let me open the file and come back. Okay, so it's requiring question 1 from climate change over here. So we have climate change. The burning of coal, oil, and natural gas, as well as deforestation and various agricultural and industrial practices, are altering the composition of the atmosphere and contributing to climate change. These human activities have led to increased concentrations of particles and greenhouse gases in the atmosphere. The relative importance of the main contributors to temperature change is shown in Figure 1. Increased concentrations of carbon dioxide and methane have a heating effect. Increased concentrations of particles have a cooling effect in 2 ways, labeled particles and particle effect on clouds. So they gave us Figure 1. Okay, we have carbon dioxide, methane, particles, and particle effects on clouds. the dark is known effect and the shaded is possible effect. Bars extending to the right indicate heating, and extending to the left are cooling. The relative effect of particle and particle effects on clouds are quite uncertain. In each base, the possible effect is somewhere in the range shown by the light gray bar. Using the information figure 1 to develop an argument in support of reducing the emission of carbon dioxide from the human activities mentioned. So, what they want, this is the answer key here. What they want is develop an argument in support of reducing the emission of carbon dioxide from the human activities. So, why should we reduce the emission of carbon dioxide? Obviously, the emissions of carbon dioxide should be lessened because they contribute the most to the heating effect. So, if we reduce them, it will reduce the impact of using these burning these fossil fuels, whatever. So you can see here, these are all sample answers. So what you need to do is carbon dioxide is the main factor causing an increase in temperature. So reducing the amount emitted will have the greatest effect in reducing the impact. So these are over here. Code 2 means you get 2 marks, which is full. Code 1 means you get only 1 mark, and code 0 is 0 marks. So these are examples. The emission of CO2 causes significant heating and therefore should be lessened. So this would get you full marks. According to figure 1, reduction in the emission of carbon dioxide is necessary because it considerably heats the earth. Again, this is 2 marks. You can read over these, and I'm pretty sure it's very self-explanatory. Page 80, 81, and 82. Let's take a look. Over here, we have ultrasound. In many countries, images can be taken of a fetus by ultrasound imaging. Ultrasounds are considered safe for both the mother and the fetus. The doctor holds a probe and moves it across the mother's abdomen. Ultrasound waves are transmitted into the abdomen. Inside the abdomen, they are reflected from the surface of the fetus, and these reflected waves are picked up again by the probe and relayed to a machine that can produce an image. To form an image in the ultrasound machine, it needs to calculate the distance between the fetus and the probe. The ultrasound waves move through the abdomen at a speed of 1,540 meters per second. What measurement must the machine make so that it can calculate the distance? This is grade 6 stuff. If you have speed and you want to find distance, speed is distance over time. How do I find distance knowing the speed? I need time, right? So obviously it must measure the time needed. So an example, they don't, okay, it must measure the time needed. These are all correct answers. The time of travel, the time, and then note this. Okay. Question 4. An image of a fetus can also be obtained using x-rays. However, women are advised to avoid having x-rays of their abdomens during pregnancy. Why would a woman avoid having her abdomen x-rayed during the pregnancy in particular? If you don't know this, the easiest thing is just say the x-ray might hurt the fetus. Or you could say X-rays are harmful to the fetus. In general, anything that has to do with X-ray being harmful, that's literally it. Okay. Obviously, because the X-ray causes radiation, and it's a small baby boy, we don't want any radiation because it might cause a mutation. For those who do biology, you should know what a mutation is. Question 5. Can ultrasound examinations of expectant mother provide answers to the following questions? Circle yes or no for each question. Is there more than one baby? Obviously, it should be yes. What color are the baby's eyes? Obviously no, because it's in black and white. Is the baby about the right size? Obviously yes, because if it's too big, it's going to show in the image. Right? So we're done for the PISA. That's it. Thank you so much for watching, and good luck in your physics CA.